Okay, project test 7, video number 3. And this is problems 21 to 30. For a school fundraiser, 600 raffle tickets were sold by students at the school, of which 88 were sold by one student, Audrey. So 88 by Audrey, this is going to be important. Of the 600 sold, 30 were randomly selected to receive prizes, and 7 of the 30 tickets selected were sold by Audrey. So Audrey sold 88 tickets, 7 of which were prize winners. To investigate how likely it is that by chance alone that at least, and by the way, this is a key word, at least 7 of the 30 tickets could have been sold by Audrey, students in a statistics class ran a simulation. One trial of the simulation is described by the following steps. From the 600 chips, assign 88 red and the rest blue. The 88 red represent Audrey. Select 30 chips at random. These are prize winners without replacement. Record the number of red chips in the selection of 30. All right. So we're going to select 30 chips. Those 30 chips out of that 600 are winners. And we're going to note how many of them are red, because if they're a red winner, they were sold by Audrey. The results from the simulation are shown in the histogram trial. All right, so we did this over and over again, and we want to know how many times that they got at least, and by the way, this is key, at least 7. So the probability that X was greater than or equal to 7. But when I look at that, we did this 1,000 times, so my denominator is 1,000. And it happened 78 times they sold exactly 7, 39 times there were 8, 15 times plus 5 plus 1. So let's add all those up together. 78 plus 39 plus 15 plus 5 plus 1 equals 138 times out of 1,000, which is 0.138. So basically 13.8% of the time, this happened by random chance alone, according to our simulation. So we have a p-value equal to 0.138, which is a pretty large p-value. Based on the results of the simulation, is there convincing statistical evidence at the significance level of 0.05? So alpha is 0.05. This is greater than, so we're going to fail to reject and say, you know what, not significant evidence. So basically, this is not going to be yes, this is going to say no, there's not significant evidence. And then we have 2 choices of no. No, because the simulation suggests that it's likely that Audrey can sell anywhere from 0 to 11. That's not sounding too good. No, because the simulation suggests that selling at least 7 would occur about 13.8% of the time. And that's what we got, 13.8% of the time. So our best answer for number 21 is E. All right, moving on to 22. As part of a study of facility needs, the administrators of a university want to estimate the percent of students who use the exercise facility on a regular basis. From the 34,000 students who attend the university, a random sample of 370 male and 400 females were selected. Of the 770 students selected, 493 students indicated that they use the exercise facilities on a regular basis. What are the population and the sample of the study? All right, so what was the population taken from? Well, the population was taken from the 34,000, the sample was taken from the 34,000 students. And it was done so randomly, so every single student could have been chosen. So consequently, we can generalize this to the population of 34,000 students. So our population is the 34,000 students, which is going to be C, D, and E. So that gets rid of A and B as answer choices. What was our sample? Well, our sample was the 770 students that were selected. So let's see. The population is 34,000 who attend the university, and the sample is whether, nope, it's not whether they're male or female. The population is the 34,000 who attend the university, and the sample is the 770 who were selected. That sounds pretty good. Let's go ahead and read E just in case. The population is 34,000 who attend the university, and the sample is the 493. No, that is not the sample. All right, the sample is the whole amount, the 770. All right, that were surveyed. Number 23, a study will be conducted to examine a new medicine intended to reduce high blood pressure in adult men who have high blood pressure. As part of the study, a random sample of 40 men with high blood pressure will have their blood pressure measured, and then they will take the new medicine every day for 1 month. At the end of the month, their blood pressure will be measured again. Oh, each person was tested twice. They were tested before the medicine and then after. Okay, consequently, because it's a before and after, this is likely going to be a paired, but let's continue reading. Of the following description, which is the best procedure to investigate whether there will be convincing statistical evidence of a change on average in blood pressure for men with high blood pressure who take the new medicine? So first off, we're doing a before and after. So we're going to say this, you know what, this is a mu D equals 0, and whether or not the mu difference before minus after is greater than 0. So I'm looking at a mean. So obviously I'm not talking about a proportion. And I know it's a mean because we're talking about a paired test. And so we're not talking about a two sample. So we have a matched paired t-test for a mean difference is the only possibility. And once again, we read carefully that they were tested before they took the medicine and then again after. So we have a before and after situation. Each individual was tested twice. We know it's not a two sample test because we do not have one group getting the medicine and another group not getting the medicine. So 23 is D. Moving on to question 24. A roadrunner is a desert bird that tends to run instead of fly. While running, the roadrunner uses its tail as balance. A sample of 10 roadrunners, so we have 10, was taken, and the bird's total length in centimeters and tail length in centimeters were recorded. The output shown in the table is from a least squares regression to predict tail length given total length. So we're predicting tail length given total length. So basically, we're working with a y equals mx plus b situation where y is tail length. So tail equals our slope. Remember, this right here tells us the y-intercept, so we're not looking at that. So our tail equals 0.5264 times the total minus our y-intercept, which is negative 1.281. So minus 1.281. All right, so when I plug in, well, suppose a roadrunner has a total length of 59 centimeters and a tail length of 31. Based on the residual, does the regression model overestimate or underestimate the tail length of the roadrunner? So let's plug in. Let's plug in 59, all right, because that's the total length, and we're going to use that to predict. So 0.5264 times the 59 minus the 1.281. 0.5264 times 59 minus 1.281. And I end up getting a predicted, and I should put a hat on this because this is a predicted tail length equal to 29.7766. So that's what I predict, but what we actually had was 31.1. So my estimate, my predicted, underestimated the actual. So we know we're doing an underestimate because this is what we actually observed, but this is what we predicted. But then they start talking about residual. So we have residuals positive, residuals negative. Well, remember, residual equal observed minus expected. Well, our observed was 31.1 minus our expected was 29.77. So 31 minus, 31.1 minus what we expected. And we ended up with a residual equaling a positive 1.3234. Okay, so our observed was greater than our expected. So we underestimated because the residual is positive. All right, the residual is positive. Moving on to 25. The distribution of assembly times required to assemble a certain smartphone is approximately normal with a mean of 4.6. So we have a mean of 4.6. And a standard deviation equal to 0.6. Of the following, which is the closest to the percentage of times between 4 minutes and 5 minutes? So that's the area I'm looking for. Now, I can do this very quickly as a norm CDF in a calculator, and I'll do that in a moment, but I want to remind you how to do this on a test for an FRQ. So Z equals X minus mu over sigma, and we want the probability that 4 is less than X is less than 5. So we're going to do the probability that Z is less than 5 minus the 4.6 over our standard deviation of 0.6 minus the probability that Z is less than 4 minus 4.6 over 0.6. And that would be our work shown on an FRQ. But since this is a multiple choice, we're just going to go norm CDF, and we're going to have a lower bound of 4, an upper bound of 5, a mean of 4.6, and a standard deviation of 0.6. So this is lower, upper, mean, and this right here is my standard deviation. So here I go. Second VARS, normal CDF, lower 4, upper 5, mean 4.6, standard deviation 0.6. And I end up getting 0.588. And my closest answer is C, which is 59%. So for problem 25, we're looking at C for our answer. For number 26, a company produces millions of 1-pound packages of bacon every week. My kind of company. Company specifications allow for no more than 3% of the 1-pound packages to be underweight. To investigate compliance with the specifications, the company's quality control manager selected a sample of 1,000 packages produced in 1 week and found 40 or 4% to be underweight. So basically, they're telling us they have a p hat equal to 0.04, which was based on an X over N, which in this case was 40 over 1,000. I'm going to back up here and I'm going to establish my null and alternative. My null is that we're at our proportion equals 0.03. The alternative, and this is where people mess up on this problem. If it's less than 3%, do we have a problem? And the answer is no. Matter of fact, they're happy if it's less than 3%. The problem is if it's greater than 3%. If we have 4%, we have a problem. If we have 5%, we have a problem. All right. But if we have 2%, everything's good. So our problem is when our proportion is greater than 3%. All right, because this is a proportion test, we want the problem, but basically we're going to work with z equals p hat minus p naught over p naught, q naught, and n. But we can do this very quickly on the calculator, but I do want to remind you what this looks like for an FRQ. For an FRQ, you're going to need to show this 0.04 minus 0.03 over the square root of 0.03 times 0.97 over a sample size of 1,000. Now be real careful with this. Make sure that you have 0.03 and 0.97 because this is a hypothesis test. All right, so running this stat test, one proportion z-test, number 5. Our p is 0.03. Our x value, in this case, was 40. We have 1,000 packages. And we're worried if it's greater than. When we press calculate. And we end up getting a p-value of 0.032. 0.032. They're telling us our alpha is 0.05. This is greater, so we're going to reject the null. And if we're rejecting the null, then that means we have enough evidence. We have evidence at alpha equal 0.05. So that gets rid of the nodes. Yes, because the sample estimate of 0.04 is greater than the company specifications. No, that is some evidence, but that's not adequate evidence. Remember, we have to compare to the alpha level. Yes, because the p-value is less than the significance level. That is why we are rejecting, and that tells us that that we are out of compliance, or we're out of that 3% range. So 26 is B. Okay, number 27. Having a little bit of problems here. All right, the histogram shows the results of 3 simulations of a sampling distribution of a sample mean. For each simulation, 1,500 samples of size n were selected from the sample population and the sample mean was reported. Which of the following is the correct ordering of the graphs from least value of n to greatest value of n? So basically we're saying, you know what? We're taking from a population, the same population, but our n changes. And remember, this is what's going to happen. The standard deviation of x bar is the standard deviation divided by the square root of n. So as n goes up, our width decreases, or our spread decreases. As our n goes up, our width decreases. So this is the narrowest. So this is going to have the biggest n. This is the widest. So this is going to have the smallest n. So, and then this is in the middle. So this is the middle one. So smallest, middle, big, smallest n, biggest n, and they wanted it from least to greatest. So least, A, next one, C, next one, B. The one that has that order is A. So the answer to 27 is A. Make sure you pay attention to what they say. Least value of N. So because this is spread out the most, it has the smallest end. Because this is the tightest, the interval is the narrowest interval, biggest end. And this one just happens to be in the middle. So this is the middle end. All right, number 28. Researchers conducted a study to investigate the effects of soft drink consumption on fat stored in muscle tissue from a sample of 80 adult volunteers. 40 were randomly assigned to consume 1 liter of soft drink each day. The remaining 40 were asked to drink 1 liter of water each day. So basically, we have 2 treatment groups, and we have random assignment. This makes this an experiment. All right. At the end of 6 months, the amount of fat stored in each person's muscle tissue was recorded. The people in the group who drank the soft drink had, on average, a higher percentage of fat stored in the tissue than the people who drank only water. Which of the following is the most appropriate conclusion? All right. This is one of those times that they're trying to get you. Read every single answer choice carefully, because they will get you on this one if you don't. There is evidence that consuming soft drinks causes more fat storage in muscle tissue than drinking only water, and the conclusion can be generalized to all adults. That actually sounds pretty good. That sounds pretty good. We're going to keep reading because that's definitely a possibility. There is evidence that consuming soft drinks causes more fat storage in muscle tissue than drinking only water, and the conclusion can be generalized to all people who consume soft drinks. No, we didn't base it on those who consume soft drinks. We just generalized, we were talking about adults. There is evidence that consuming soft drinks causes more fat storage in muscle tissue than drinking only water, and the conclusion can be generalized to whom? Adults similar to those in the study. This is always the case. We can only generalize to what is similar in the study. This gets rid of A. C is right now the better choice because it's similar to the adults in the study, and this was to all adults. Well, those in the study might be different than all adults, so similar to the study is a better choice. Although cause and effect cannot be established. Oops, it was an experiment. We like cause and effect. It can happen. Although cause and effect can, oh, no, it's an experiment. So our best choice here is C. If you just, I mean, it'd be very easy to stop at A when in fact C is a better choice. Okay, moving on. Number 29. A random sample of 1,018 city residents were asked to rate their level of support for a proposal being considered by the city council. The table shows the responses by level of support. Okay, so here we have 336, very supportive, 387, 295. We have 1,000, our sample size is 1,018. Based on the responses, which of the following is a 95% confidence interval for the proportion of all city residents who would respond very supportive or somewhat supportive of the proposal? Very supportive or somewhat supportive. So in this case, we are looking at 336, or p hat, equal to 336 plus 387 over 1,018. So let's add those up real quickly. 336 plus 387 equals 723 over 1,018, which gives us a p hat of 0.71. So our p hat equals 0.71. Now they want us to construct a 95% confidence interval. Well, confidence intervals are basically following this formula. P hat plus or minus Z star P hat Q hat over N. So my P hat is 0.71. So that gets rid of these first two. Plus or minus Z star, we'll get to that in a moment. This is 0.71 times 0.29, that's 1 minus 0.71, over 1,018. And I need to calculate my Z star for 95%. So second vars, inverse norm, parenthesis, 1 minus 0.95, close parenthesis, divided by 2. Mean is 0, standard deviation of 1. And I end up getting 1.96. So let's calculate this by hand, and then I'll show you how to do this on a calculator. Because you're going to want to do both methods, or some of you are going to choose this method, and some of you will want to do it by calculator. So 0.71 times 0.29 divided by 1018, and I'm going to take the square root of that number, caret 0.5. Now I need to multiply that by the 1.96, and I end up getting 0.0278. So this tells me my answer choice is D. Now, for those of you who wanted to do this by calculator, you certainly could have. Stat, test, one proportion, Z interval. So we're going to have to scroll down a ways until we get to letter A. And my X is going to be 336 plus 387. My N is 1018. And I wanted 95%. Everything looks good to go. And I get that value. Well, real quickly, I see my P hat, and that's good news. Because there's my P hat, so I know it's going to be C, D, or E. But I have a problem. I don't know a margin of error. But I can solve that real quickly. So it doesn't matter which one of these I take. I'm going to choose the upper one, which was 0.738. That's my upper bound minus my P hat. So if I take my upper bound minus my P hat, so 0.738 minus 0.71, what do I get? 0.738 minus 0.71 equals 0.028. All right, and that's probably the quickest and easiest way to go about doing that. It's not the only way. I could have also used a lower bound and I would have gotten a negative value, but nonetheless, it still would have been 0.028. So that's a couple different methods to work that problem. Regardless, E is the best choice. And if you're doing a FRQ, you're going to need to show your formula and your plug-in. Okay, number 30. A manufacturer of cell phone batteries claims that the average number of recharge cycles for its battery is 400. A consumer group will obtain a random sample of 100 of the manufacturer's batteries and will calculate the mean number of recharge cycles. Which of the following statements is justified by the central limit theorem? All right. So to be central limit theorem, in our sample, which n equals 100, needs to be greater than or equal to 30, which it is. So the distribution of the number of recharge cycles for the sample is approximately normal because the population of 400, no, not because of the population mean, but because our sample size is greater than 30. The distribution of the number of recharge cycles for the sample is approximately normal because the sample size of 100 is greater than 30. The distribution of the number for the sample, no, not for the sample. The distribution of the number of recharge cycles for the population is approximately normal because the sample size of 100. The distribution of the number of recharge cycles for the population is approximately normal. Now, we don't know about the population, all right? We don't know about the population. We don't even care what the population is. What we care about is not the sample, not the population. We care about the distribution of the sample means. So I'm looking for something about the distribution of the means, or distribution of the X bars, or distribution of the sample means. The distribution of the sample means, hey, this sounds better, because we're not talking about the sample, we're not talking about the population, we're talking about sample means. The number of recharge cycles is approximately normal because the sample size of 100 is greater than 30. The problem with this one was it didn't say sample means. The distribution of the sample is going to follow the underlying population, all right? The population is what it is, but the distribution of the sample means becomes normal by central limit theorem. So 30 is D. Please read all of your answer choices. Remember, distribution of the sample means is normal by CLT for n greater than 30.